I wanted to spend a little bit of time in this video talking about some reciprocating engines, things that you might find like in a car, but also in a lot of other types of settings and situations. So you spent a little bit of time in this last homework digging into some of the calculations, how these actually work. We're not going to do calculations like this for full engine cycles anymore this semester. So this past homework was your one time getting to do the full cycles. We'll maybe do compression processes, expansion processes, and piston cylinder arrangements, but just not the full cycle. What I did want to do though is spend at least a few minutes talking over the cycles that you did, but then also several cycles that we didn't do that I think it's interesting to know a little bit about. So the first cycle that you did, problem 1 on the homework, was an Otto cycle. This is the standard internal combustion engine where we have a spark ignition. So we would have something like this where going from what I have labeled 1 to 2, we have our compression process. Then from 2 to 3, our piston doesn't move, but we have a step in terms of the thermodynamics, and that's where we have what essentially is an instantaneous combustion because we have our spark plug, which sparks the air-fuel mixture and causes it to combust, to explode. That explosion, or that input of heat, that input of thermal energy, which is really what's happening, that causes an expansion event. So that drives our expansion here from 3 to 4. We expand, then here at 4, we have our hot exhaust gases. And in the Otto cycle, the one that you solved, from 4 back to 1, we have essentially a constant volume heat exchange. So we are cooling down, so temperature is going down and pressure is going down from 4 to 1. Now, practically what actually happens is we exhaust our gas and have an intake of fresh air from outside. So if you think of what's happening with the piston, if I just erase my scribbles here, what's happening with the piston, it's going down, up. So down, up one time. And then from here, 4 to 1, it's going down to push out the exhaust gases. And then it's going back up again as we intake new air. So this would be 1, this would be from 4 to 1, 2. So we have down, up, down, up. It takes 2 of those cycles, or 4 strokes, in order to get all the way around this thermodynamic cycle. But it's not even. It actually takes a full 2 strokes to get from 4 up to 1. That's an Otto cycle, probably the one you're most familiar with. Another one that should be fairly familiar just from everyday life, but also now from doing some of the calculations behind it, is a diesel cycle. So the big difference between a diesel cycle and an Otto cycle, this compression process is essentially the same. But in a diesel cycle, we have a higher compression ratio. So what we've learned is that the compression ratio, the difference between, say, the pressure at 1 here and the pressure at 2, that difference in pressure, or the ratio, changes how much of an increase in temperature we would expect to see. So, a factor of 10 increase in pressure will not give us as high of a change in temperature as a factor of 15 or a factor of 20 increase in pressure. So in a diesel cycle, we have a higher compression ratio. And what that does is gives us a higher temperature after the compression here at 2. We design a diesel engine so that it gives the right compression ratio where when basically our hot gas here at 2 is just going to spontaneously combust. So in a Otto cycle, we have a spark. that leads to combustion. In a diesel cycle, we just keep compressing it until it combusts. So that changes the dynamics of the combustion process a little bit, where the Otto cycle combustion was essentially instantaneous. It happened, there was no volume change. The piston basically didn't have time to move. Now in a diesel cycle, we have what is essentially a constant pressure process of combustion. So as we combust, the temperature is continuing to go up. The pressure is staying about constant, so that means the volume has to go up. So we have a volume increase, so we're actually getting work out in this process here from 2 to 3. Then after that, it looks a lot like the Otto cycle. We continue with the rest of our power stroke, and then we have a full 2 strokes, 1 cycle down, up, for our piston to finally exhaust our gases. So that's the diesel cycle, again, one that you might be familiar with. A cycle that you're probably not familiar with is the Atkinson cycle. Maybe you've heard of it. I would guess many of you haven't unless you're really a car person. But this is the cycle that's used in many modern cars, especially hybrid cars. So if you have a Prius or if you have some other hybrid car, I'd encourage you, go on to Google, search for your car model thermodynamic cycle. You can probably find somewhere where somebody explained it. It probably is an Atkinson cycle. I used to have a hybrid car. It ran on an Atkinson cycle. This is super close to an Otto cycle, so I just want to explain a little bit the differences. So the compression process here from 1 to 2, exactly the same as a normal Otto cycle, the normal spark internal combustion cycle. The actual combustion, again, exactly the same. So this is the same as Otto. The expansion is what's different. Basically, we allow our expansion to keep going farther. So if you look here, the volume of gas here at 1, we are actually a larger volume here at 4. So our work is related to the pressure and the change in volume. So a bigger change in volume means we get more work out of our engine. A smaller change in volume from 1 to 2 in our compression process. So from here, we have a smaller volume change. That means we have to put less work in. So the net effect is that we get a more efficient engine, a more fuel efficient car, but we sacrifice some of the volume of our engine. So we basically, for the same size engine, we get less power. We get less horsepower. So better fuel efficiency, less horsepower. We can look at a video from Toyota. So Toyota, obviously the maker of the Prius, they have a nice video explaining a little bit how this works and showing how functionally you can actually make an engine that does this, where the compression stroke and the expansion stroke are different volumes. So we'll flip to this video from Toyota.
The Atkinson cycle is a method of internal combustion first proposed by English engineer James Atkinson in 1882. The Atkinson cycle uses a different thermodynamic process than the traditional Otto cycle common to most gasoline engines. Toyota hybrid vehicles all operate using the Atkinson cycle, and some non-hybrid Toyota vehicles are able to switch between the Atkinson and Otto cycle as needed. The Atkinson cycle is more fuel efficient than the Otto cycle, but this efficiency comes at the expense of power output, which is why it has not been widely adopted. However, Toyota has overcome this shortfall in 2 ways. In non-hybrid vehicles, the engine can seamlessly switch operation between the Atkinson cycle and the traditional Otto cycle instantaneously when the driver demands more power. In hybrid vehicles, the reduced power output of the Atkinson cycle is overcome by pairing it with an electric motor. The electric motor works together with the engine and delivers additional power stored in the hybrid battery as needed. In a traditional engine using the Otto cycle, the compression and expansion strokes are equal. However, the Atkinson cycle holds the engine's intake valves open longer. This results in some of the air-fuel mixture being forced back into the intake manifold. This delays the start of the compression cycle and reduces the volume of air-fuel mixture in the cylinder. As a result, the expansion stroke is larger than the compression stroke, which allows more energy to be extracted from the burnt fuel before exhausting it out the tailpipe. With the intake valve open during part of the compression stroke, the piston also encounters less resistance as it moves upward. This reduces the engine's pumping losses, which is power consumed by the operation of the engine itself as it pumps air and fuel in and out. For both hybrid and non-hybrid vehicles, the use of the Atkinson cycle allows fuel efficiency to be optimized, while Toyota's innovative engine management systems and hybrid powertrains eliminate any compromise in performance. The features and functions.
Okay, and then they just talk about how their cars are the best. Toyota's not the only one to use the Atkinson cycle, actually most. Yeah, as I said, hybrid cars generally will use it for exactly the reasons that they described. You get better fuel efficiency, and in a hybrid, that's obviously what you're going for, but you also have, the key is you having that battery to get extra power when you need it. The last cycle that is quite interesting is the Stirling cycle. So the Stirling cycle is an external combustion cycle rather than an internal combustion cycle. So I'll go through the steps here and then we'll watch another video. In a Stirling cycle, going from here 1 to 2, the compression step is not a delta S equals 0 step. It's actually a constant temperature step or an isothermal step. Then we go from here, we add heat, going from 2 to 3, but we actually add heat from an external source. So we're not burning something here in the piston or in the cylinder. We're actually having some sort of heat source from outside of the cylinder, and we're putting heat into the cylinder through some sort of heat exchange process. So that gets us from low temperature up to high temperature and higher pressure. Our volume stays constant. Then we expand. Again, normally we would think we're expanding, temperature and pressure both go down together, but this is a constant temperature expansion. So pressure goes down, but we keep putting heat into the system so that temperature does not. Temperature stays constant even as pressure is going down. Then we have a constant volume temperature change from 4 to 1. So we're cooling the gas down and lowering the pressure, keeping the volume the same. Kind of a weird cycle. We'll watch a video and then talk a little bit more about this interesting external combustion cycle. Hello and welcome to Tea Time. And as we do tea time here in the Christian's household, we get out our trusty Stirling engine and turn some of that heat into useful work. So what I have here is a Stirling engine. So you can see as I spin the top, you can watch the piston go up and down. So essentially what's going to happen is we're going to let heat go through this from the bottom, where we're going to be at a constant high temperature, to the top where we're going to be at essentially a constant low temperature. So we have these metal plates which should stay at basically a constant temperature and help us get our heat transfer. So I'll put that on my cup of tea. It's going to take maybe a second to warm up enough. So it has to warm up that bottom plate. And then, oh, that might be backwards. There we go. So we give it just enough to get it going. As it warms up, maybe my tea here is not warm enough. There, it looks like it's going. So as it heats up, it will continue to speed up. But we can see that as the piston's going up and down, it's spinning. This is the type of engine, a Stirling engine, that it's not an internal combustion engine like your car. It's actually an external combustion engine because our heat source is actually outside of the piston. So we have the two pistons, they're both, but our hot and cold temperature are both outside of those. So essentially running what is as close really as we can make to a Carnot cycle. These are kind of nifty little engines that can use external heat sources to be able to create power. So as you watched in the video, the cool part about Stirling engines, they don't actually need a combustion process. So I was running my Stirling engine off my cup of tea. So maybe, as I have written here, external combustion engine. The combustion part is a little bit maybe of a misnomer. External heat engine, I guess, would be the correct way to say it. So these are engines which, as you saw, can run off very low temperature differences, just the difference in temperature between my tea and the room. They're useful in situations like that. Generally, they're lower power, but they can be higher efficiency. So lower power per size, so they tend to be big but low power. They can be higher efficiency. So there was actually in the 80s, NASA had a program where they were trying to build Stirling engines for cars. So the idea would be you would burn your gasoline, but you wouldn't burn it inside of the cylinder. You'd burn it outside, and then you'd have big heat exchangers which bring that energy into and out of the cylinder. Kind of a wild process. Your engine would definitely look different than what engines look like today. They were actually able to put that into real cars. There's some papers where they present some of their results, and we're able to get about a 30% increase in the fuel efficiency of an actual like real car compared to a standard Otto cycle. Again, as you heard me say, like keeping the top here at one temperature at a low temperature. So this would be all at TL. This would be all at TH. It's essentially a Carnot cycle. So this is really the closest that you can get to running a Carnot cycle. It's super, super challenging to actually design Stirling cycles that actually begin to approximate Carnot. So there are issues and problems with actually designing this and doing this, making it work as I have drawn here. But kind of nevertheless, Stirling cycle engines are interesting because they're used in potential higher efficiency applications, and because you can use them outside of combustion. So these are used sometimes more recently in what we call combined heat and power applications, where you have some sort of heat source that you use for something else. Maybe this is a heat source that you're using for a building. You can use a Stirling cycle engine to use some of that high temperature heat, turn it into work that maybe you can use to power your building, and then use the waste heat to heat the building, rather than using that high temperature heat to heat directly. We can get some work out of it first. So ways to kind of improve efficiency of larger systems like that. Obviously, you can run these. There are attempts using solar thermal heating to run Stirling cycle engines using a solar thermal source, or with geothermal. So a cycle that's a little bit more obscure, but definitely interesting. These aren't the only cycles. There are other cycles as well, the Miller cycle, the Ericsson cycle, and other twists and tricks on these as well. But these are kind of four that I think are interesting, and hope you enjoyed learning about them. As I said, we're not going to have Stirling cycles or Atkinson cycles. Like, these aren't going to be on exams. But it is interesting to see where some of the ideas and techniques that we can use to understand thermodynamic cycles, how varied those thermodynamic cycles can be and how each individual tweak can better situate that cycle to our specific applications.